tell you what, yeah, I'll tell you. This is section, you're asking about section 4-3, not 4-4. I'm going to go through 4-4 and maybe 4-5, probably just 4-4, the confidence intervals and student t distribution. I'm going to use PowerPoints, but I'll do, how about this? How about that problem 4-3.4? That's, all right, because I put that up there, right? Let's do this one. So this is 4-3.4. Michael, you asked me about this, and I don't think anybody else did, but it's a problem without a solution in the book, but it's a good problem because it actually gives you a density function. So the logical question is, why are we doing this if we have the density function? It's to set the stage for what's coming next with confidence intervals. So here they give you f of x is equal to really e to the minus x u of x, or, I mean, for x greater than 0 and 0 below that, all right? That's a density function. Then they ask for, I forgot the actual wording on this, but how many samples are necessary so you have a certain level of confidence, you want the variance of the variance to be less than 5%, something like that, right? The standard deviation of variance. Yeah.
Did you assume a step function?
Well, if it say f of x is e to the minus x for x greater than 0, and then 0 below it, that's u of x, isn't it? See, u of x is 1 for anything greater than 0, and it's 0 for anything less than 0. So it effectively gets rid of that second condition. You all with me? I'm not trying to do anything funny here. Okay. Next, can you read that?
Yes. It says, how many samples are required to estimate the variance of this time function?
Variance of s squared, right? Variance of the variance, right?
With a standard deviation that is 5% of the true value if an unbiased estimator is used.
All right, so it's 5%. This is 0.05 of sigma squared, is that right? We can, of sigma squared or squared. This has to be of the order of sigma to the fourth on this side for this to work. You all with me on this, class? You know why, right? Are you with me on this? How many took a look at this problem? I'm curious about it. It's a good problem. But the problem is they give you everything right here. We don't need to do all that stuff. Who cares about the rest? If we have that, we don't need to sample. In other words, everything that we get is we're trying to accurately figure out the statistics of this. If we have this, we don't need that. But in the next section on confidence interval, you'll see why he's doing that. Just go with me on this one. So anyway, I mean, does everybody follow me? This sigma is the true variance, right? Now, we have this, right? And I did this. I'm going to go ahead and do it again. So if you wanted to get the first, second, third moments and stuff like this, by the way, what is this? This is going to be equal to n, the number of samples, n minus 1 squared. This is from the formula. It's in the book that he kind of derives, hand-waving derives. U to the fourth minus sigma to the fourth, right? Here, sigma to the fourth, that is sigma squared squared. It is the true standard deviation to the fourth power of the actual event. But we have the statistics for the actual event. U to the fourth is the fourth central moment. And what that is the expected value of quantity x minus x bar to the fourth power. And I'll talk about that in a second. But you all with me on this? I'm just going through the motions here. Now, I mean, are you with me, everybody?
What does that mean?
The u to the fourth is the expected value. It's the fourth central moment. So the expected value of x minus x bar. X bar is the mean to the fourth power. Y'all with me? I mean, we'll do this in a second. I did it a couple different ways. Let me tell you the first way. I just used this itself as the information. So I see that I need sigma to the fourth, and I need u to the fourth, right? So here's what I did. First, I got the moment. You can do it this way, and with modern calculators, it's trivial. To get the average value, it's the integral from 0 to infinity of x e to the minus x dx. That is an integration by parts if you want, right? But your calculators will do that in a heartbeat, and that's simply equal to 1. I'm going to do it another way. This is the way I prefer to do it because, in my opinion, it's quicker. It's by simply saying, well, I know that the Laplace transform of any function in x, and this is only good for everything greater than 0, so you can do this, integral from 0 to infinity of, and this is going to be the first moment, or well, yeah, I'm sorry. I'll just do it of f of x. Let me do it this way. F of x e to the minus sx dx. That's the Fourier transform of the density function. You all with me? Right? Okay, then if you take a derivative of this, I think everybody knows what I'm doing here. I did this. Now when you do this, you get an integral from 0 to infinity of minus x times f of x e to the minus sx dx. I've done this several times, and you can see just by multiplying by a minus sign here, I go ahead and I get the first moment. You all with me? If I set s equals 0. That is the first moment, or that is the expected value of x, or it's just x bar. I'm just doing this. I want to make sure that I don't leave anybody behind if you haven't looked at this in a while. With me? That's first moment. What's second moment? Anybody?
X squared.
Take another derivative, right? So second moment, or really, or the expected value of x squared. Now, you don't have to do it that way. You can go right here and multiply this by x squared and do the integration. It's an integration by parts again, but you can do it, or you can do it on the calculator, right? It goes from 0 to infinity, has exact bounds. You can do it quick. But when you do this, what is this? This is really going to be just the second derivative of f of s with respect to s squared, evaluated at s equals 0. That would be the second moment. The negative sign will cancel at that point. You don't have to multiply by negative. All right, these moments are all going to be positive, by the way. If you get a negative moment, you forgot a minus sign. What's the next one? Third moment. I think I put all this down. It's what? It's going to be minus the third derivative of f of s with respect to s cubed, right? S equals 0. And I put this in here. And the fourth moment, that's going to be equal to, now it's the fourth derivative of f of s with respect to s to the fourth. S equals 0. And those are all the values. We'll do this in a second. I'm just showing you this is how you would get the different moments just by using the Fourier transform or Laplace transform and taking derivatives. Now, I got to say this. If this had something values that were non-zero for x less than 0, then you would have to use the Fourier, right? Because this Laplace here is a one-sided Laplace. It's not defined below that. You all with me on this class? There is a two-sided Laplace, but you don't learn about that because 99.999% of all engineers start the event at t equals 0. I mean, they're wise enough to know why make your life tough and have values starting at t equals minus 10 or something, or minus infinity. So this is what happens. Now, back to this problem. I can tell you the x bar equal 1, but I'm going to do all this. I'm going to erase that. We're going to go through all these things kind of quickly and then do this entire problem. I want to answer any questions. Hopefully I am as I'm going along. So, by the way, how many do these integrals just by multiplying this by x to the n? Anybody on your calculator? You do that? You can do it, right? Matter of fact, it's kind of nice for the fourth central moment to do that because you don't have to multiply it all out like I did.
It's hard with the S period. Mine doesn't do it with S period.
No, this is not for your calculator. This you wouldn't use on a calculator. This you do by hand because it's easy. That's the reason I'm showing you this. All right, so anyway, let's go get these values. So I need all the moments if I'm going to expand this. You don't have to do it this way, but I'm just going to go ahead and do it real quick. This is kind of, I don't want to waste too much time on this. So if I take f of s of this, the Fourier transform of that is simply 1 over s plus 1. Does everybody agree with that, by the way? You always, I mean, x is like t when you do a transform. X is a dummy variable. It goes away. Then when I take the derivative of f of s with respect to s, right here, I get what? Minus 1 over s plus 1 squared, right? Now I have to multiply this by a minus sign, and I have to evaluate this as s equals 0. and I have to multiply it by a minus sign, and then I get the expected value or the average value, right? Expected value of x. I'll call it x bar. So if you evaluate that at s equals 0, it's 1. And that will work out if you do the integration as well. So it's 1. What about x squared bar? That's the second moment. Well, now I take a derivative of that with respect to s. You all with me on this, guys? Derivative of this, and I put the minus sign back, by the way. You should put the minus sign back, right? Take a derivative, there's a minus 2. It's like s plus 1 to the minus 2 with a minus sign. So that becomes minus 2 times minus is plus 2. So this becomes 2 over s plus 2 cubed. Evaluate at s equals 0. That's going to be 2. Do you all agree there? Going through the motions, right? So what's the third moment, guys? No, I mean, what do? You take a derivative of that, right? And then you multiply it by a minus sign. So I'm going to get 2 times 3 is 6, right? You multiply this by a minus sign, but I'm going to get rid of it over s plus 2. This is going to be to the 4th power at s equals 0. This is going to be simply equal to 6. And what about, huh?
Yeah, it's s plus 1.
That's s squared, right? First moment. Second moment, s cubed, right? Third moment.
Yeah, but s plus 1.
What?
In the denominator.
Oh, yeah, yeah. Sorry. Jeez. What's wrong with me? My bad. I think I'm in a hurry. I mean, everybody agrees with it. I apologize. I'm sorry. Ready? All right. Finally, the fourth moment is what? Take a derivative of this, right? Now, we should multiply this by a minus sign. So you get 6 times 4 is going to be 24 over s plus 1 to the 5th power. Pardon me, it won't matter there. S goes to 0, and this becomes just 24. We've got all the moments, correct, class? Now, over here, how do we get this? First, let's get the variance, okay? So how do you get the variance of the real function? This is the real variance, right? The true variance. So that's equal to what? X squared bar minus x bar squared. I'm doing it this way. You don't have to, but it should make sense, and I'm doing it for a reason, because you can fumble these things sometimes if you're not careful. So what's that going to be? Well, isn't that 2, I think, right? Yeah, 2 minus 1 squared is just 1. Agreed? Correct? So that means we have this right here. Now we need this fourth central moment. You can do it a couple ways. I want you to listen to me on this one. If I want the fourth central moment, I did it both ways. If you have a calculator and you want the central moment, the expected value of x minus x bar to the 4th power, you could take the integral of x minus x bar to the 4th power times e to the minus x dx from 0 to infinity, and that x bar is just 1, right? And you can get it that way. Your calculators will do this. I did this. Did anybody else do this? This will get you the fourth central moment, the u to the 4th. You all agree with that? This is u4. Or how can you do it? And this is the way I did it. I'm going to erase this so I can do it here. I don't mean to go too quick on this one, but this problem's pretty good because it shows you a lot of alternative methods. Your calculators will do these moments darn quick. I mean, if you have any modern calculator that does symbolic stuff, even non-symbolic, you can get this stuff fairly quickly. You don't need to do all this Laplace transform stuff. But I like to see this because on a test especially, it might be much quicker to do it with Laplace transforms if it gets complicated. So anyway, then I need this fourth central moment. And I know what that is. It's the expected value of x minus x bar to the 4th power, right? Do you all agree with that? So I'm going to just take this x minus x bar, x minus x bar. I'm going to square it. That's x squared right here, minus 2x x bar. And then it's going to be plus x bar squared, which is a constant. Now I'm going to square that again in a second, right? Because this is x minus x bar squared, right? But first I'm going to put in the values that we have. So this is pertinent to our problem. Over here, what do you get? Well, that's still x squared minus 2x x bar. X bar is 1, so it's minus 2x. And x bar is 1 plus 1 here. You all agree with that? Now I have to square that again. Follow me? Because I need this value first. So when I square that again, I'm going to erase this. Here you can take a look, and the way I do these, you can do them any way you want. You take all these terms and you multiply them by itself first. So I get x to the 4th, right? Then I get minus 2x times minus 2x is plus 4x squared. 1 times 1 is plus 1, right? Now I knew normally I have this and I'll have this again multiplied by itself. So I'll have x squared times 2x and then minus 2x times minus 2x. So I'm going to get plus, if you think about this, I'm going to get 2 times, and this is going to be, this times this is going to be minus 2x minus 2x cubed. Do you all agree with that? Hopefully I did it right. And then finally, I'm going to have this 1, right? If you think about this, when we multiply again, then I'm going to have this times 1 and this times 1. So then I have plus x squared minus 2x. And it should be minus 2x. This should be times, let's see, let me just do this in my head. So this is really minus 4x, right? And this is going to be 2x squared, right? You all with me on this? I'm trying to go through this in my head, but it'll work out at the end of the day. So if you come over here and then simplify, you have x to the 4th, right? And then you have minus 4x cubed, right? X cubed bar, minus 4x cubed. Now let's see what we get here. It takes care of that and that. I know I've done this one. Then for x squared, I got 6x squared, right? And that takes care of this and this. And then I have minus 4x plus 1. I believe that's it. Correct, class? All right, now, and I'm trying to go quickly on this. I don't want to go too quickly. I really need the expected value of this. So just bear with me, because I want this. So when I look at this, u to the 4th, the expected value of that thing, can everybody follow me where I'm going with this? Why I did all that? Because I have all the I have all the moments up to the 4th moment. That's in terms of all the moments, not central moments. You all with me? So here, what do we get? The expected value of x to the 4th, I think, was 24. I hope that's right. Minus 4 times the expected value of x to the 3rd was 6, right? So that's minus 24, which is great. Then I have plus 6 times the expected value of x squared. I think that was 2. So that's 12. And then I have minus 4 times the expected value of x, which is 1. So it's minus 4. Just correct me if I mess up. And then I have the expected value of 1 is 1. Did you have a question? Oh, no. All right. You all agree with that? And that is what? Let's see. That cancels. I get 8 and 1 is 9. It looks like it's 9. Is that right? All right, 9. Now I come over here. I've got everything I need in. Do this on your calculators. You're the one that called me out because I was doing this and I didn't type it in right. I had 322. I think it's
3202.
3202. Okay, I think this is it. So when you look at this, over here I have 0.05, and this is going to be sigma squared. What is sigma again? Sigma is 1, or sigma squared is 1, right? Times 1. And this is squared is equal to n over n minus 1 squared. And this is u to the 4th, which is 9. We got 9 minus 1. So this becomes 0.05 squared equals n over n minus 1 squared times 8. And at the end of the day, if you solve this, you should get a very large number, like 3202 about, and you should get a very small number, almost 0. There's 2 roots to this one. You all with me, class? Anybody else do this one? Did you all get that? You get a very small, almost 0 value. You can't, you neglect that. So n equals 3202 for this to be within the actual variance of the variance to be within 5% of the variance, if that makes sense, of the variance of the population. But you had to calculate all this stuff. Now, the other way to do it, and I mentioned this just a little bit ago, the other way to do it is just take your calculators, use this as f of x, and if you want the really the average value, just take this times x, integrate it out in your calculators from 0 to infinity, you'll get 1. I've done this. If you want the central moment, I mean if you want sigma squared, pardon me, if you want the actual standard deviation, or the actual variance, then you take x minus 1, square it, and multiply by e to the minus x and integrate it from 0 to infinity. You will get 1. And then if you want the fourth central moment, you take x minus 1 to the 4th power times e to the minus x and integrate it from 0 to infinity. And you will get, what do we get, 9, right? You'll get them. I did this last night. Did anybody else do all this? I made sure everything, huh?
I did it the way you went, and I didn't do it that way.
I did it both ways. And I made sure if you go any which way, you'll do it. Your calculator sometimes will do it faster if you have, if you can do these integrations quickly. But the Laplace transforms are pretty nice. The problem I always have is sometimes if you need like the 5th, 6th central moment, these things really blow up. This one's not that bad, but they can blow up, and I think everybody knows. It's a good review of some of the techniques we talked about earlier for finding mean, second moment, and all this stuff, so I wanted to do that.
What's the percent of a real good problem in today's context?
I'm thinking about making a really good problem. Suppose I make that e to the minus x squared times a constant, and you have to calculate first the constant, then everything. Wow.
Oh, well, you set it equal, you do the derivative and set it equal to 1.
You what?
You do the derivative and set it equal to 1.
Of what?
Of the...
I'm saying if the density function here is e to the minus x squared u of x, you're thinking of making it a Rayleigh, right?
I notice you take a derivative to get the max. I don't know what it is, I forgot.
We don't need them. We need first, second, third moments, all right? The Laplace transform of that is a little trickier. It's actually e to the, I'm not going to, what?
You said get the constant.
Yeah, for starters, but you have to also do one. I mean, complete the problem. I didn't do this on the quiz, so don't freak. What if that's the problem?
Oh, that just, yeah, you have to.
You can do it. You can do it with Laplace transform tables. So you want to take a guess what that is?
Oh, wouldn't it be?
That's a Gaussian. It becomes a Gaussian in the other domain. I promise you. I'm not going to go into that now. We did a problem just like this. Remember that crazy one? You were on the right track where you had to do what? You had to first take the derivative of that, then take the Laplace transform of the derivative. Do you remember how I did that? Remember? And then, all right, when you take a derivative of this, you get 1. Minus 2, right? X, it's going to be minus 2x squared e to the minus x, right? And then you're going to get what? Plus plus really what? I mean, that will be the derivative, but the u of x you have to take a derivative of. You get an impulse function, all right, at x equals 0. In the long run, then you have to take the Laplace transform of that because it's a derivative. You get a j, or Laplace, you get a minus s out in front, but I don't want to confuse you going down that route. But that's how you do that.
Wait, I mean, if there was it was, for instance, k e to the minus x ux.
Yeah, suppose it's k. Then you can integrate this thing out from 0 to infinity, find k, right? Set it equal to 1. If you wanted k. Suppose we got k. Now how do you do it? Then to solve this problem we just did, what I need is first, second, third, fourth moments, right? In other words, we need the Laplace transform of that. The Laplace transform of that, you can actually find this value without going through Laplace transform methods by taking first the derivative of that and then take the Laplace transform of the derivative. I'm not going to go there right now. I'm just going to tell you you can do it.
That's a great question. I like that.
You like that? We'll make it even a little more fun too.
Oh, how do you do that?
I'm going to add another probability, another e to the, say x e to the minus x with another constant L on it.
I don't see that on there.
I'm not going to do that. I'm not that evil.
I would be screwed. I would get up and leave.
Just turn don't even turn the paper, just leave it on the desk.
You know, I had a prof years ago. He's a very, very bright guy. He was Illinois physics guy. He was our department, extremely bright, theoretical kind of physicist. And he held a patent on stealth technology on the SR-71. He's a very, very bright guy in electromagnetics. So this is an advanced electromagnetics course. It wasn't, I don't think it was doctoral level, but from this, we're studying like crazy for this. Separation of variables and all the coordinate systems. We're trying to figure out how to match boundaries and all this. He says prove and mathematical statements and functions. We never did a proof. I'm thinking, you got to be kidding me. I mean, I talk about want to get up and leave. You know, mathematical proofs have to be exact. Admittedly, the book did some of this. Man, that caused a lot of angst. In other words, when a professor asks a question that has nothing to do with anything you've done, other than contextually, maybe the book mentions something about this, especially in engineering, throws a curveball at you, you're really having a hard time. And I did. I hope that answered your question. That's a good problem because it takes a long time. There are a lot of parts to it. It's not a quick hitter. And it also forces you to think about it. However, the most important thing that I see in that one is if we have the density function, why are we bothering figure out how many samples we need? We've got the problem solved. It doesn't matter. You all with me? But it's to set the stage for the next part, which I'm going to get to now. All right? I mean, does anybody have any other questions? I want to get to this thing. So, and I'll bring up some other things that you'll see the benefit of knowing this, okay? There'll be some benefits, I hope. Let me first get this thing on. I'm going to start here, and I'm going to try to do this in a meaningful way. I got a lot of stuff, a lot of information. So we did all these homework problems, including 4-3.4 just now. You with me, class? Can you hit those? Can you all see that? I won't even dim them if you can see. You good with this? Everybody? All right, next part. Now we're doing this, I like what he says. Suppose we have a random sample or a random waveform of infinite duration, equally spaced samples. Assume the waveform has a true mean of 10. This is in the slides. And a true variance is 6. What is the variance of the sample mean? Now this is just sigma squared over n, right? Do you remember that? And hopefully that's what it'll have. Yeah, that's the variance of the sample mean, not the variance of the samples. It's not the variance of the variance, pardon me, right? So that's the variance of the sample mean we get. That is a statistical function. Then he goes on, how many samples do we need to estimate the mean, not the variance squared, within 2% of its true value? It's a no-brainer, right? 0.02 on the other side, right? Times the actual variance, standard deviation equal to n over 9. And I think he says that. There it is. Can everybody follow me on that? We did this in section 4-2, right? Just take a moment, convince yourself. There's nothing tricky. Now, that's where you got an infinite number of samples coming at you all the time. And you're sampling a set. Say they come at 100 every minute. You're taking out of that, 10, or how, he doesn't even say it. Now we're going to take 225 out of that. Say it's 10,000 minutes. In other words, we're going to sample this at a constant rate. But if there's a finite number of samples, and you want to figure this value out, then what do you have to do? Now it's going to be standard deviation, or variance, right? Sigma squared over n, but then it's times capital N, the actual sample set, minus n, that's the sample size that you're going to have, over capital N minus 1. Do you all remember that? That's destructive testing one. Want to make sure you do. All right. Then, this is good. And I'm going to talk about this. Suppose we use n equal 225, so that's our sample, that's the number of samples, and compute the sample mean. Are we guaranteed that the mean of our value is within 2%? Now, let me just take a moment and try to set the stage for the next part without flying through. When you think about this, the actual sample mean this is the sample mean, has a density function, x hat bar of x, right? And I call it sample mean here. You all with me? It is a probabilistic function. You all with me on this? Now, if you take a look at that and say this is the actual mean of the population, the true mean, and you look at this, it's going to have a distribution that could be Gaussian, and if there's smaller and smaller number of samples, then it goes to something called the student t. Everybody with me on this? Now, if you look at this, and we talk about confidence intervals in a second, we're going to figure how wide that margin is about the mean to have a certain level of confidence in what we're talking about. Now, let me explain this in my own way. When I think about a confidence interval, these are the limits. It's going to be x minus the lower limit and x minus the upper limit. This is that, and this is this. This is the area. So if they said they want a 90% confidence, what is the 90% confidence interval of the sample that suppose you sample this set with a certain number of values, that your sample mean is actually 90, it's got a good chance, 90% chance we're right, that we're within these margins of error. You all with me, class? Well, we have to calculate that area. Do you all agree? And then, we have this area, so it's 0.9. Now we have to calculate this spread here and here. That's the idea. Find this alpha value. Find the limits, all right? That means we use the tables again, but now we're going to have the value of this integral, and we have to figure out what argument gives you that value. For this function itself, let me just get to the chase here. Normally we had z equal to x minus x bar, and this was over sigma for z. This was back in the day. Do you all remember that when we did all this stuff? And then we looked up something called the characteristic function. You can use characteristic or q of this z, and that was equal to the integral from minus infinity to z, and then it was all normalized for the fz of z dz, and this was the characteristic function tables. Do you all remember that? I'm not going to write the Gaussian, but it's a Gaussian form of this thing. So if we wanted a 90% confidence interval, we would take this at x bar plus this and then subtract x bar minus that and set it equal to 0.9. And we have to find out what this value would be. Do you all with me, class? All right? Or really what this value is. And when we normalize all this, then we get this density function. Now it has a zero mean, and it does this. And then we can go up and below the actual 0 point, right? And this would be a function of z. This would be 90% or whatever percent we want. I'm not doing this exactly for a reason. I just want in your mind it should make sense. If we can find out what the density function is for this mean, then we should be able to figure out what the spread is in the actual confidence interval, whatever it is, 90, 95. If you wanted, y'all with me on this, guys? Okay. So this is going to get interesting. Now, the only reason I did it that way is I don't want to go just to the student t or just to the Gaussian, all right, or any other possible distribution. I wanted to say for any distribution, if we can get the probability density function, then your gut feel. If we have that, if we want to know what the bounds are for 90% of that function, or 95, it would be wider, or whatever, we can do it. Do you all with me? And by the way, the more samples you get, you're going to find out the narrower this becomes. And then the limit as it goes to infinity goes to 0, basically, because you're going to have sampled the whole population. There'll be no variance. And we'll use that. Okay, so keep that in mind. And he said, are with true, no, okay, that means if we, what we just did back here, when we calculated the number of samples so that the variance of the sample mean is there, are we within 2% of the actual sample mean? The truth is no. And here's how he goes through this. Now he says, what is the probability of the mean value of the samples? So this is a statistical variable that's within 2% of the true mean. So we need the density function. That's what I was getting at. You all with me? We need the statistical density function for the x hat. And here's where we get into some interesting things. So we start with 225. By the way, how many looked through this? Just tell me. If you haven't looked through that, pay attention here. It should make sense. Remember, the key is we have to know the density function, the statistical density function that goes with the statistical mean of the samples. This is the key. It's either going to be Gaussian or it's going to be something called student t when the number of samples is small, less than 30. You all with me, class? Roughly less than 30. Okay. So take a look at this. We say the sample mean is 10. And the variance of our samples mean, this is the variance of the sample mean is 0.04. But we knew sigma squared, which is troubling. If we knew that, we got anything we need. Basically, we were ready. If we got the mean, the standard deviation, we got anything we need. But he's trying to set the stage for where he's going with the student t distribution. So what is the probability? What does it say? 2% of the mean. All right, so we're going to be 2% is 2% of this. If the mean is 10, it's either below by 2% is 9.8 or above by 10.2. Do you all agree with that, class? It's one way or the other. Do you agree with that? So now this is the density, or is the characteristic function. It's the integral from minus infinity to that value, or this is the symbol. And we take the upper limit minus the lower limit. Do you all follow me? That would be the area in between that I'm showing you. And that would be, now we use the old technique where we have, this is just, it's the value we're going to minus the mean. This is the value we're going to less the mean. But the 2 over here is interesting, or 0.2. That is this. It's the square root of this right here. Square root of sigma squared over n. So square root of that is 0.2. Do you all see that? The way they do it is they put s, if it's just actually the sample mean that we use for the student t, or they use sigma over the square root of n. So sigma was 9. Sigma squared was 9. Sigma would be 3. And the square root of that, so this is 0.04, square root is 0.2. Now you all remember remember we took x minus x bar over sigma before, correct, class? Remember, now that sigma is really going to be this. It's the variance here. You got to take the square root of it, because now we're talking about the samples themselves, the variance and then the standard deviation of the samples. You all with me? How many understand this? Take a good look. You're going to see this, I hope, but it should not be that troubling based on what you've done before. You come down here and you see that this is the number, or the area in between the lower and upper limit, the 2% limit, right, that we set of the mean. It's only a 68.26% chance that we're in that range. That's not very good in my opinion. But you see the method. Can you all follow me on this? If you don't, there's probably little things you need to confirm in your understanding of this. Okay. Now we get into some interesting. To answer the questions like this, we need to know the probability distribution of the sample mean. The normalized sample mean, now this one right here is what I was talking about. That means you know the actual sample mean and the actual sample variance, the z thing. You all see that? But you'll notice the standard deviation is always divided by the square root of n for the actual standard deviation of the sample mean that you use in the calculations. It's important you don't mess that up. You with me? Now, down here, this is called t. It's just the argument we're going to see of the student t distribution. Did anybody look at this at all? All right, student t is interesting for one reason. Guinness Stout is where it came from. You know what Guinness Stout is? How many do? God, if you're college kids, you don't know what Guinness Stout is, it's a bad day. It's beer. I mean, you really didn't know Guinness Stout was beer? Guinness Stout. I don't know how you pronounce it down here, but it was called Guinness Stout where I was from. Anyway, it's booze. It's beer, and it was made, and the guy that figured this out the student t distribution worked for them because he needed the statistics of the actual sampling they were doing for the brewery. Now, they can't sample every single ounce of beer. So what they do, they make vats of beer, and they take a small amount, in other words, a small number of samples of the vat, and then they test them to see what do they call that, the specific gravity is, the amount, percentage alcohol, and they figure out there's other characteristics. So it's going to be a small percentage of the total is going to be sampled, and they're different vats, so they don't have some kind of continuous thing. And I'm not a person that's a master brewer, but I understand there's a lot to this, and they have to do the sampling correctly, so they know when they ship a product, it's not going to be a disaster where you get a huge variance. Okay. So this is how you would do it for the student, the argument of the student mean distribution. I have to say this. You can see the similarities. This is the same as this, except now we're going to actually use the variance of the samples. Y'all see that there? That is the sample variance. It is not the true variance. N is still the number of samples, but you'll notice they have the true mean there, which we're going to talk about in a second. X bar is true mean. So if the samples are independent and sigma is known, why are we doing this? And the sample size is large, or xi are Gaussian. So if you got a whole bunch of samples, or the samples are guaranteed to have a Gaussian distribution in their statistics, you know, the probability of one versus the other value is Gaussian, then the mean of the samples is a true mean, and the variance of the samples is just sigma squared over n. That's non-destructive testing. I hope you can appreciate this. Second, the normalized mean also of, it says if the normalized sample mean is also Gaussian, you can use this. In other words, now you basically have the ability to go right, and you can actually use the known standard deviation and the known mean, the simple number of samples there, and you can calculate z. And you'll notice that the confidence interval is always about z equals 0 because you're subtracting off the average value there. This says, what if the sample size is large and sigma squared is unknown? This is important. So we don't know. This is more real. We don't know, right? Can we use s squared as an estimate? Sure. You can use s squared as an estimate of sigma squared. When when n is large, the variance of s squared should be small. That means there's not much difference between the true variance and the variance of the samples. That's the only thing he's saying there. If you look then, the normalized Gaussian sample mean is approximately this. You can still use Gaussian stuff if n is large. However, instead of sigma there, small sigma, now use s, standard deviation of the samples. All right, he does this one. 100 bipolar transistors. Wonder where you got that. And it's got a mean of 120 for current gain, and it's got a actual variance of 25. What is the probability the sample mean is between 19 and 121? Now, take a moment and think. Well, it sounds like I'm going to take z equals x minus x bar, right? Divided by the standard deviation, right? And you can see here, he hasn't given us the number of samples, right? So it is the true standard deviation. Do you all follow me, class? So for this one, here he does it. Oh, I'm sorry. He says the sample is 100. I'm sorry about this. So just hear me on this. This right here is just the difference, right? It's 119 minus 120. He gives you 120 as this, so this is going to be a minus 1 on top. This is a plus 1. Can anybody tell me how you got the 0.5? That's what? The square root is sigma squared over n. Remember that the variance of the samples was equal to sigma squared over n? So sigma was, or sigma squared was 25, right? So square root of that is 5 over square root of n is 100, so over 10, so it's 0.5. That's how we got these values here. You all with me? I'm trying to get through this without confusing you. So that's how we got that value. So when you take a look at this, he wants the probability of that z that was before there. It's just taking x minus x bar over In this case, it's going to be the effective standard deviation, which is square root of 25 over 100, or square root of 1/4, which is 1/2. And here you get, well, this is the characteristics 0.2 minus the characteristic function of minus 0.2. Do you remember the characteristic function of a minus value is just 1 minus the characteristic function of the plus value? So you end up with 2 times the characteristic function of 2 minus 1, or this is the actual probability, almost 95%, right? That's the way to do this, and this should ring bells. You've done something like this several times. Now, here's the student t thing. What happens when the sample size is small and sigma is unknown? Well, this is good. So the normalized sample mean is this. Now remember, this is going to be called the student t distribution. Did anybody read why it's called the student t, by the way?
Wasn't it because they weren't allowed, like Guinness has a rule against taking credit?
Yeah, Guinness, the distributor or the brewery, had a policy that nobody could publish anything under their own name. So he used, his name is capital S, student, and he published this. But it was correct. It's actually kind of an interesting thought. The gamma function we're going to talk about, do you know who figured out the gamma function long ago? It wasn't him. Bernoulli, you know, the name Bernoulli? And so he used that to develop these statistics. It's an interesting, I went through all that, and I was fascinated by how he did that. So it won't be Gaussian even if the samples are Gaussian if the sample size is small. And we got a random variable of the mean, and it's divided by another random variable. So this is not going to be Gaussian, in other words. Small sample size, unknown standard deviation. All right, hold on. There we go. You've had to see this, and I pronounced it wrong. So now, if n is small, less than 30, this is important, sigma is unknown, but xi are Gaussian. So if we knew they're Gaussian, we could still, then this student t distribution will be this. But you'll notice that that's the normalized sample, and it has a student's t distribution with n minus 1 degrees of freedom. I don't like this degrees of freedom business. You see this symbol here? I'll get to the student t above it in a second, n minus 1. What do you think about when you hear degrees of freedom, anybody?
Ability to be off.
Usually I think emotion, or I think of something that is in the physical world. If you talk about 1 degree of freedom, it can move in x, one direction. 2 degrees, it can move in x and y. 3 degrees, x, y, and z, and so forth. Or with rotational stuff like aircraft, it can have yaw, pitch, and roll, if you know what I'm talking about there. So that's what I think about. They use it differently here. Degrees of freedom are just the number of samples minus 1. Why he chose that, I was reading about it, and this gamma function business has to do with a function that satisfies one concept. If you have all these points knitted together, it will find a way to get a trajectory through all these points using something called a gamma function, and it'll never go through 0. That's the only thing I'm going to say about the gamma function. There's a lot more to it, but just appreciate the fact it solves a mathematical constraint of a lot of problems. So here's something else. This f of t, that's the density function for the normalized t. Do you all hear me on this? All right, you have to know the degrees of freedom. So you have to know the number, and you have to know a normalized function. The Gaussian function is plotted here, and the student's t distribution is plotted here for similar values. But as the number of samples or the degrees of freedom gets large, they'll overlay. They're indistinguishable. When you hit about 30 or more samples, you can't tell the difference. So just use a Gaussian. Do y'all hear me on that? 30 or more, it's basically the same thing. Now, what is this? This is the gamma function. Did anybody look this up? Gamma function is actually defined in terms of an integral. It's the integral, I'm not going to go on this, it's t to the n minus 1 times e to the minus n. I forgot the actual, I've got it written down here, but it's a crazy, crazy integral. Let me find this thing. I'm only going to mention it. I thought I did. Well, you can look it up on Wikipedia too, or look it up in your book, but the gamma function solves, where is that thing? Yeah, it's equal to, it's the integral from 0 to infinity of t to the z minus 1. Sorry, it's gamma function if the argument is z, of z minus 1 e to the minus t dt. So it's a confounding integral, all right? But it's got some relationships that are neat, and I'll spend more time on that. So anyway, here's a couple of things to just note about the gamma function. I didn't plot this. It plots in the complex plane. You can have arguments of the gamma function, the real and imaginary values. So just appreciate that. I'm not going to do it right now. So in general, the gamma function of k plus 1 is just k times the gamma function of k. And this is the nice part. It's just k factorial. If k is an integer, which is nice, because that happens a lot. Also, if you think about the gamma function of 1, it's the gamma function of 2. Think about k factorial. And it's equal to 1, and the gamma function of 1/2 is square root of 1/2. Now, this is the way you can derive a lot of values by using this recursive relationship. And so let me go ahead. I'm not going to spend much time on this. So if they just want the value of the student's t distribution for the argument equal to 1 and 4 degrees of freedom, it's just plug and chug this. By the way, your calculators have the gamma function, I think, if you look it up. It's G-A-M-M-A. It's usually a capital G. I believe you have it there. And they'll allow arguments that are real and imaginary, but we're only going to talk about real arguments. So the only thing he's doing here is allowing you to calculate a single value of the density function. It has nothing to do with anything of importance yet, just to get familiar with this gamma function business. After that, here's the student's t's distribution. This is in your book on page 436. I will provide you that if you need it, when you need it, okay? Everybody on this one with me? Finally, oh gosh.
So basically you're saying we'll have a problem similar to this on the final exam?
On Monday, you're going to do your homework and I'm going to go through them? Yes. Okay, but I need to get to the point. All right, you can read this stuff. I'm going to give you problems. I did all the problems in this section. They're not bad, but I need to give you a quiz. I'm looking at the time now, okay? So I'm going to give you a quiz. Then we're going to, I'll pick it up from there. Please do the homework. Come Monday, it's the last class, and I didn't even get to do the problems I wanted, but that's on me. I figured, can you do me a favor? Fill up this row